So here's section 2.4, which is on acceleration. Our goals here are to understand the significance of acceleration and how it affects velocity. So we're going to define acceleration essentially. And we're also going to interpret some graphs to find information on acceleration from those graphs. Let's start out with a definition. So what is the equation for average acceleration? Well, average acceleration, or acceleration in general, by definition, is a change in velocity over a change in time. Essentially, how rapidly your velocity is changing as time goes on. So you can see our equation here has the average acceleration as the velocity per time, or a final velocity minus initial, over that time interval. Now let's see what you remember about acceleration. Is acceleration a vector or a scalar? Does it include direction or does it not? The answer is, it is a vector, meaning that it does in fact have a direction that goes along with it. Your acceleration could be to the north, to the south, it could be right or left, positive or negative. All those things are ways to define the direction of your acceleration. So what are the units? Units on acceleration would be any type of length or distance divided by a time squared. So if we put this in SI units, our SI units for acceleration would be meters per second squared. Basically, how you're changing your meters per second each second. So over a given trip, your average acceleration isn't always the instantaneous acceleration. It could be changing as your trip progresses. Instantaneous acceleration is going to be looking at the acceleration at one particular instant or moment in time. So if average acceleration is a change in velocity over a change in time, really when you want to get to an instantaneous acceleration, you want to limit that time interval so that it becomes infinitely small and you're essentially looking over one single instant in time. And you'll notice in this equation here that that's exactly what we're doing. When we take that limit of the change in velocity over the change in time, that limit really is a derivative. So that change in velocity over change in time now becomes the first derivative of velocity with respect to time, or you could also write that as the second derivative of position with respect to time. Graphically, this is going to be the slope of your velocity time graph because again, derivatives are representative of slopes and a velocity time graph can now give you the acceleration in that slope. So if you had information on velocity and acceleration, how could you tell something's speeding up or slowing down? The basic rule is that if they have the same sign, both velocity and acceleration going the same way, that object would be speeding up. So let's say that you had a velocity maybe pushing over to the right, and you're moving this way. Think of your acceleration as an extra push, as a force that's going with it. If acceleration was going the same way and also pushing you in that same direction, that object would be speeding up. If you were moving to the right, but your acceleration was working against you and pushing in the opposite direction, that object would be slowing down. So if they're going the same way or velocity and acceleration are working together, that object is speeding up. If the velocity and acceleration are working against each other or have opposite directions, that object would be slowing down. Now let's look at this graphically. Looking at this graph, we want to look for places where the acceleration is positive, where it's negative, and where it's zero. So let's zoom into the graph a little bit here and take a bit of a closer look. We can see from the beginning, we start out with a zero acceleration, or a zero velocity, and that velocity is increasing. It's getting faster and faster and faster in this positive direction. If the object is moving with a positive velocity and getting faster and faster, we know that this means this object should have a positive acceleration here. On the other hand, when we look at this portion of the graph, we can see that the object starts out with a very high initial velocity here, but that velocity is getting lower and lower and lower until eventually it reaches a zero velocity down here where it crosses that axis. In this case, if your velocity was moving in a positive direction but slowing down, this should correspond to a negative acceleration. Basically, acceleration had to be working against your velocity to cause you to slow down and eventually come to a stop. What we find on this side of the graph, or for this leg of the graph here, you started out with a zero velocity and your velocity was increasing in a negative direction until you got down here at negative 40 meters per minute are the units on this particular graph. Now if you're speeding up in that negative direction, that would mean that speeding up corresponds to an acceleration that is going the same way. So a negative velocity would correspond to a negative acceleration if you were speeding up in that negative direction. We can see over here on this leg of the graph that you are getting closer and closer to a zero velocity. This piece of the graph would correspond to a positive acceleration. And if we come back over here and look at this section of the graph, we can see that it flatlines there, or basically you're maintaining your velocity and the velocity isn't changing. That would mean that you have a zero acceleration. Now let's look at another way that you could figure out where you would have a positive and negative acceleration. If we look at acceleration as being the slope of our graph, we can see that I could have come up with those answers very easily just by looking at slopes. Let's look at it in a different color so that we can go over it one more time and talk about these accelerations. On this portion of the graph, we can see that we have a positive slope. That's where we said positive acceleration made sense. When it flatlines and you have a zero slope, there's where we said you had zero acceleration. And everywhere we had this negative slope, we said our acceleration was also negative. Over here, slope became positive again, and it corresponded to a positive acceleration. So if we look at this in terms of slope, positive slopes give you positive accelerations, negative slopes give you negative accelerations, and a horizontal line or a zero slope would give you a zero acceleration. Let's try out creating our own graph here. Let's say that at time 0, you had a velocity of 30 meters per second. And just a couple of seconds later, you were down to a velocity of only 15 meters per second. So we start here at 30, and over the course of 2 seconds, we drop to 15. If we looked at our change in velocity over our change in time, we would see that we would get a negative acceleration here, because when we take the 15, or the final velocity, minus the 30, or the initial velocity, over our 2-second interval, we're going to get a negative acceleration. Again, from our graph, we can see that this negative slope can show us that that acceleration would be negative just by looking at the graph. So one more time, your general rule for deciding how you're going to speed up or slow down: if velocity and acceleration are in the same direction, that's an object that's speeding up. When velocity and acceleration are in opposite directions, that's going to be an object that's slowing down. So do you remember what actually causes an acceleration? Think back again to your regular physics class. Anytime an acceleration is there, the other thing that must be present is a force. And that force will always be proportional to your acceleration. So whatever direction your force is in, your acceleration is also going to be in that exact same direction. Basically, force and acceleration are going to line up. So let's try an example problem together. We have a particle that's going to be moving along the x-axis, where its equation for its velocity at any time t is equal to 40 minus 5t squared. We're going to start by finding the average acceleration from the time interval 0 to 2 seconds. So we know the velocity of the object at any time is going to be this 40 minus 5t squared. And we also know that if we wanted to find an average acceleration, that average acceleration is going to be a change in the velocity over some sort of a time interval. Now, finding the change in velocity is going to require that we use this velocity equation that we have here given to us in the problem. If we wanted to know the velocity of the object at time 0 seconds into the motion, we would simply take this equation and plug in 0 as our time, giving us an initial velocity of 40 meters per second. Looking at the 2-second point in time, we could again go to our equation and we'd plug in 2 seconds worth of time. And we'd find that in this case, when we plug those numbers in, our velocity is 20 meters per second. So if we wanted to find this average acceleration by looking at the change in velocity over the change in time, our change in velocity is going to be our final velocity minus the initial velocity all over the time frame of 2 seconds. Plugging that in, we can see that our average acceleration for this particular particle is going to be negative 10 meters per second squared. If we were asked a second question and asked to find what the acceleration is at exactly 2 seconds into the motion, here's where our derivatives can come in handy. We know that an instantaneous acceleration is going to be the limit as our time interval approaches 0, or basically as this number down here becomes an infinitely small amount of time. Really, this means that we're looking at the derivative of the velocity equation with respect to time. So if I take this equation and take the derivative of the 40, or a constant, is going to be 0, and the derivative of negative 5t squared is going to be negative 10t. So if I wanted to find the exact acceleration, or the instantaneous acceleration right at 2 seconds, I could simply take this equation and plug in the 2 seconds time frame, or the 2 second point in time that I'm looking at, and I could find that right at 2 seconds into the motion, my acceleration at that point in time should be negative 20 meters per second squared. We'll practice with more of these types of equations in class and give you some homework problems to try them out yourself, but hopefully this gave you a brief introduction as to how you could use the general equation or definition of acceleration to find an average acceleration, and also use some of your calculus skills to use derivatives and find an instantaneous acceleration.